Okay, so welcome back. We're going to be solving another question from the chapter 4 of engineering mechanics by Meriam. In this one, we need to compute the force in link AB of the lifting tongs, which cross without touching. We're going to go with our equilibrium assumption, and we need to dismantle the system first of all. And what I'm going to do, I'm going to draw the free body diagram for this part of this system. And what we're going to do at point D, if we look at it, we'll see that we have a two force member DE, which means our force will be along this link ED. We can call it D. And we also have another two force member, which is the link AB, and that's what the question is asking us. So we're going to consider one force AB, and we have the forces at point F. We're going to consider two forces Fx, Fy, and we have our equilibrium equation. Sum of all forces in X equals 0. Sum of all forces in Y equals 0, and we're going to have one moment equation. Obviously, right now I'm drawing the free body diagram for member FBD, so the blue shaded area is the free body diagram of FAD, and we are writing our equilibrium equation for this specific member. So what we can do, we can start with our equation for this member, but if we look at it, we'll see that we have 1, 2, 3, 4 unknowns, which means we can move on to another member to just figure out some of these unknowns. And I'm gonna draw the free body diagram for this box, and we can see that the figure is symmetrical, so whatever we have on the left half of this figure is going to be the same on the right side too. So if we draw the free body diagram of the box, so what we're going to have is the weight of this box, which is 800 pounds. And obviously we have two forces on the left and right, and we can consider two forces in X direction too. So we can call them Fy. The other side, we can call it Fy or Gy, again, because of the symmetry, they are the same forces, Fx here, Fx here too, but like for this one, if we just do sum of all forces in Y equals 0, we should be able to find Fy, because we're going to have 2Fy minus 800 equals 0, so Fy will be 400 pounds. So now that we have this, we can use this information in the previous part. And keep in mind that Fy is upward in here, which means it has to be downward in the member FAB because of the Newton's law, same force, just in the opposite direction. So now that we have Fy, is easy enough to find the Y component of the D. I'm just gonna, so if we try to resolve this force, it's gonna be dx and this is gonna be dy. Finding this angle is pretty easy because we have all the dimensions. Let's just call that angle alpha. So the tangent of alpha would be the opposite, which is 12 divided by 18. So the alpha would be tangent inverse of that value, 12 over 18. Let's see what we get. So tangent inverse of 12 divided by 18, that's going to be 33.69 degrees. And the reason I did that is because if we use our y equation equals 0 for this free body diagram, again, everything is color coded. So the blue writing is for the free body diagram of FAB, and the yellow was for this. So basically we have dy minus Fy equals 0, which means dy is Fy, which was 400 pounds. And we know this is equal to d, the y component would be sine of alpha. So we can find the force D in here, which is 400 divided by sine of 33.69. So we figure the D, the only unknown in here now that we are looking for is FAB. And if we just do the, actually it's not the only unknown because we have FX2, but we don't care about that. if you just find the moment about point F, counterclockwise positive, we should be able to find the FAB. So we're going to have the moment of FAB, which is a clockwise moment. So negative FAB times the distance. So the distance or vertical distance from F to the line of action, which is 24 inches. And we're going to have the moment of the dy. As we can see, it's a counterclockwise moment. So dy was 400. So plus 400 times the distance is the distance we have from F to the line of action of the D, which is basically this 30 inches plus that little distance that we have in here. And for finding that, we know this distance is 15 and we have this distance 18. So if we just subtract those, we're going to get this little distance, which is going to be 3 inches. So plus 3. And we're going to have the moment of the y component, or the the x component, the cosine of the angle, which was 33.69. We figure out the d, this is going to give us 600, and the distance for this one is also pretty easy to find. So we have 20 plus 24 equals 0, and this should give us the FAB that we are looking for. So 600 times 44 minus 400 times 33 divided by 24. So 600 times 44 minus 400 times divided by 24. Sorry, I have a positive sign in here. And yeah, this is going to give us 50 pounds for the force. So the direction for the FAB is actually correct, which means the member AB in here will be in tension. Based on Newton's law, this has to be in the opposite direction of this force. So the member is in tension. And yeah, that's the final answer for this question. Hope everything is clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.